So first, the results of the poll. 26 students submitted. There was overwhelming response to no, meaning majority of the class prefers not to have Friday quiz going forward. Okay. So here's the announcement. I said initially that we will have a quiz today, so I'm going to change that. We won't have a quiz today, which is week 6. Then next Monday is a holiday, so we only have 2 classes. So next week also we won't have a quiz, but we'll have one final quiz on in week 8, which would be the quiz from today. Okay, so FETs and MOSFETs are something. Well, it's a topic that I do in the class in 306, simply because, well, it's a fundamental, requirement for the syllabus and all of that. But also fundamental knowledge is required, but it's not going to be assessed separately on the exam. Okay, so I won't have a quiz on FETs or MOSFETs, but in week 8 we'll have a quiz that will be based on BJTs. Okay, so this week no Friday quiz, next week no Friday quiz, but we'll have a quiz in week 8. That will be the final one. Okay. Let's see. Yeah, that's the only announcement I had to make. Okay. All right. So one last page in FETs was the saturation region before we get to BJTs. So we saw in MOSFETs how we can apply a voltage at the gate. We create a, we obtain a channel right below the gate. When you apply a voltage between the drain and the source, you have current flowing through that channel, which is right here, right from that channel. That was in the triode region or the linear region. So you have free current flow going between the drain and the source. But now, if VDS keeps increasing, right? Here we have VDS value small. That's a lower value, which would be in the triode region right here, right? This would equate to VDS small. Now, as you increase VDS, the channel begins to pinch off. And when VDS is equal to VGS minus VTN, channel begins to cut off. Okay, channel begins to cut off. So what happens to the current flow? And in FET, when the channel pinches off, what happens to the current flow?
The current remains constant.
In terms of physics, what happens to the electrons or charge carriers that are present in the channel? We say the channel is pinched off or pinch off, but electrons are still injected, and a similar effect takes place here. Even though the channel pinches off, what happens is the depletion region is now increased, and so the electric field that is associated with the reverse with the depletion region also increases. Because of this, the electrons that were flowing or initially present in the channel are now injected or pulled into the depletion region. So there are electrons here. Those are free charge carriers. They would continue on and get injected in the depletion region. So right here, we would say electrons are pulled or injected into the depletion region. And once they're pulled into the depletion region, they come under the effect of the drain source voltage VDS. Because drain is held at a positive or higher level, the electrons are attracted to the charge and current still keeps on flowing through the device. But it approaches a limit. Okay, it approaches a limit and the current saturates. And so in the triode region, we saw that it behaves like a voltage control resistor, and the current and voltage have a linear relationship. So in the triode region, it's linear. Then as VGS increases, pinch off, flattens out, and it saturates. So this is VDS, and this is ID, drain current ID or drain current. And of course, when VGS is equal to 0 right there, channel is already pinched off. I'm exaggerating this effect. This is when VGS is 0 volt. Unlike the JFET, there is no channel that is present. VGS must be applied to create a channel, right? So VGS is equal to 0. It's right there. This is the linear region or the triode region. And this is where it cuts off or saturates. This would be for VGS far greater than 0. Okay. So the physics of operation is very different between the JFET and the MOSFET. However, the resulting characteristic is very similar. Okay. Yes. Yes. Right there. Well, it depends on the device, whether it's N channel or P channel. If VDS, so let me understand. The question being asked is if VDS was greater than the absolute value of the pinch off voltage. Pinch off region. Let me see. If value of VDS was greater than, excuse me, greater than the pinch off voltage, it would be VGS greater than threshold voltage. Is the channel present or not in your question? Yeah, so then current would still be flowing. If there is a channel, whether it's pinched off or not, current would still be flowing. By its very definition, it's an enhancement mode device, meaning we have to apply a gate voltage for a channel to be present. So by its definition, if you say pinch off, then there must be something to pinch off. A channel must exist to be pinched off. If a channel does not exist, there is no pinch off. Does that make sense? Because this is not a depletion mode. In the depletion mode JFET, a channel already exists by its very fabrication. And so you apply a voltage to turn the channel off or to turn the device off. Here, a voltage must be applied for a channel to exist. So if we say pinch off, well, then a channel must exist for pinch off. Otherwise, there's no pinch off. So if there is pinch off, that must mean that there was a channel. And if there was a channel, that means current flow is present.
Where MOSFET differ from JFET is there doesn't matter the kind of speed that's done by flow either.
No, because no, JFET, you have a channel present. In a MOSFET, we need to apply VGS. If VGS is not applied, there's no channel. Now, there are depletion mode MOSFETs, but this is an enhancement mode MOSFET. This is what pretty much all MOSFETs would be. Enhancement mode.
The IV characteristics from what you're saying.
Yes.
Like should
It's very different, two very different devices. It's the effect of an electric field, hence a field effect transistor. The device physics is an operation is very different. It's completely different. Anyway, 11:21. Okay, that was the last slide. Well, actually, there's one more slide, but there are different kinds of symbols of the MOSFETs on here. So it's just a summary. When you take a look at your own time outside of class, these are the symbols that you students must become familiar with. Not all of them, but at least the primary ones, right? We have a enhancement mode NMOS and PMOS, right? Those are the ones that we want. That's right here. Enhancement PMOS and enhancement mode PMOS. Those two. The arrow goes in, it's NMOS. Arrow goes out is a PMOS. And then there are other ones that you can take a look at later. For now, I want to turn my attention to chapter 4, which is BJT. Bipolar junction transistors. And I mentioned this earlier. Okay. The name bipolar comes from the fact that the current flow is a result of both the minority and majority charge carriers, meaning holes as well as electrons. Okay. Holes as well as electrons. BJT was one of the first, the first electronic solid state device that was presented. Okay. So BJT consists of two p-n junctions. So it's a sandwich layer of two p-n junctions. If you have an n-type material sandwiched between two p-type materials, we have a PNP transistor. If a p-type material is sandwiched between two n-type, we have an NPN transistor. Okay. And the symbol for both is shown. Depending on the current flow, if the arrow points in, it's a PNP. Okay. And if it points out, it's an NPN. And the arrow notes the emitter terminal. And we'll talk about all those terminals in just a little bit. Okay. C stands for collector. B stands for base. E stands for emitter. So similar to the MOSFET devices and the JFET devices, you have three terminals. For JFET and a MOSFET, straight lines. For a BJT, it's angled. Okay, it's angled. The arrow notes the emitter terminal. The base is always in the middle. So if you know the emitter, you know the base. The third terminal is the collector. All right. Next few slides we'll go through a little bit quicker. This is a slice of an actual BJT. You might have this packaging of a transistor in your lab kits. This probably looks like this. Unless it's a metal can packaging. But and then you have three leads coming out. This is the top. And looking at it from the front. Okay, looking at it from the front. I want to create a sort of three-dimensional structure. It might look something like this. And something like this. Okay. So this was a image of a NPN transistor. You can still see the number here. It's a 2N3904. The 2N means it's two junction device. 2N refers to all transistors. Okay, any device that has two junctions. Diodes are always 1N because it's one junction. So 2N simply notes it has two junctions in there. Anyway, this transistor 3904, the actual transistor is not even this. Let's take a close look at that one. The actual transistor is right here on top. Okay. The rest of this is simply the bulk of the wafer. Okay, but the actual transistor is just on the top. The shiny thing right here is the metal that makes contact with the back side. And the front side, of course, we have a gold bonded wire to make connection to our device. Looking at it from the top, that's what it would look like. If you fabricate this, whether it's discrete or whether it's in a integrated circuit in a microchip, this is looking at it from the top. The top view. You have the emitter in the center right here. These lines are simply contacts. So whatever you see here, these are simply contacts. So draw actually it's too much work to just have a different color, but these are metal contacts. And that's another metal contact right here. Okay. The actual device, of course, is underneath inside the silicon wafer. So here's a simplified cross section of a BJT construction. You have the entire device made out of a N-type material, and that is the collector. It's the largest or the biggest structure physically. Okay. Then we create a P-type material inside our N-type wafer. So now we have base. This base is very thin. And then inside that P-type material, we create another N-type structure. And that N-type structure is by far the smallest of the three, but it is the most heavily doped. And the base and the collector are lightly doped. Okay. So the JFET and the MOSFET are symmetrical devices. The BJT is not. And the reason for that is, of course, the physical construction as well as the doping concentration. The emitter is the smallest structure. The collector is the largest. However, the emitter is also the most heavily doped structure, and the base and the collector are very lightly doped. Okay. Again, doping means the number of free carriers that are present in the semiconductor. So here's a three-dimensional view of the construction. the physical construction, we would have a collector. So all of this is the collector. Okay. These are just metal pads making contact. Making contact with the structure. The actual device is right here where it says N plus. Okay. The N plus simply refers to the doping concentration. Okay. The plus sign simply refers to a slightly larger or higher number of charge carriers compared to the other structures. Okay. So you have the base, and then you have the emitter inside the base, just right here. Okay. This entire section would be the base. And of course, then the emitter inside it. We'll look at the device functioning in the next couple of slides. But again, here is a cross-sectional view or side view. And from here, we can see a little bit of the basics. We have the collector and the base currents both combining to give us the emitter current, IE. Okay. All right. In terms of operation or physical construction, sorry, not operation, in terms of physical construction, we can simply state it's two back-to-back diodes, right? It's two back-to-back diodes. So depending on the biasing that we apply, these junctions would either be forward bias or reverse bias. Right? It's simply two back-to-back diodes. And if that's the case, then it should function like a diode, right? That's what we would expect. So if you apply a forward bias to the base emitter PN junction, it should work as a regular diode. Same thing if we do for collector and the base, right? And that's what the expectation would be, but that's not how it would work. The terminals, the terminal characteristics would be defined with the terminal voltages, and that would be VB, VC, and VE. And then the currents would be IB, IC, and IE. Two of the most important voltages would be VBE and VCE. VBE would mean the voltage measured at the base with the reference at emitter, and VCE would be voltage measured at the collector with reference to the emitter. Okay, measurement would be plus here, minus here, plus here, minus here. Whether it's a NPN transistor or a PNP transistor, we always still refer to it as VBE and VCE. That would not change. Okay. All right, so in a solid state BJT, this is how it would work. We'd have a voltage applied between the collector and the emitter. There's a current flow between the collector and the emitter. And similar to the FETs, we use a third terminal, the base, to control the flow of that current. Okay, so there is a voltage between collector and emitter. Current flow results from the collector to the emitter. And then the base controls the flow of current from IC to IE. So in a way, we can say that IB controls IC, because IC and IE are going to be very close in value, approximately equal to value. Okay. If you apply KCL, if you treat the transistor as a single node and you apply KCL, we can write that the emitter current is the sum of both the collector and the base currents, IC plus IB. However, IB is typically very, very small. Typically in microamps, okay? And so for many cases or many analyses that we perform, we tend to ignore IB. And we can write IC is approximately equal to IE. The ratio of IC and IB is known as the current gain beta, which is by far the most important parameter for a BJT. Okay. That's amplifying effects. In reality, what's happening is we have a voltage being applied between the collector and the emitter. And then if you apply an AC signal at the base, then the collector current, the collector to emitter voltage takes on the shape of the AC input signal. And you get an amplified output. Okay. It's simply an illustration of what occurs when you have IB and IC coming in. But let's look at the device physics operation. We'll look at these equations in just a couple of slides. Okay. So, all right. First thing about this is that it is not to scale. Right? It's not to scale. We have the collector to the right, you have the emitter to the left, and you have the base in the middle. This is an NPN transistor. One thing again I'd like to point out, here it says N++. It's subjective, okay? N++ or P or N+ simply means that's a slightly larger concentration, or it's a larger concentration than a quantity that does not have a plus sign. How large? We don't know. It simply indicates it's higher, that's all. That's all it means. So it says here, P-type material, it must have some doping concentration, then it's N+ in the collector. That means the doping concentration is larger or higher than the base, and the plus indicates it's the highest. It's just subjective, it's relative, that's all it is. All right, let's take a look first at the emitter and base junction. What do we see? If you have a diode, N and P, and you forward bias this diode, what is happening in terms of device physics? There's an there's a NP junction. It's a diode. You forward bias the diode. You have electrons and you have holes, and you forward bias it. There's a depletion region in the middle. What happens? Exactly. Yes. So you have majority charge carriers flowing across the junction, right? So a forward bias PN junction result in majority carrier flow. So that's what would happen in a BJT. If you take an NPN transistor and you forward bias the emitter base junction, the majority charge carriers from the emitter are going to cross over into the base, and the majority charge carriers from the base, meaning the holes, are going to cross over into the emitter. How about the reverse bias junction? If you have a N and a P device, what happens here? Reverse bias PN junction, depletion region expands, but we still have current flow, right? And that current flow is due to, well, yes, is due to minority charge carriers. And the name of this current is the reverse saturation current, or IS. And it's small because it's due to the minority carriers, which are not, the sheer volume of the minority charge carriers, the name suggests, is very low. Hence, the resulting saturation current is very low. So now, if you apply this device physics knowledge to a BJT, what happens? If the emitter-base junction forward bias, you have the electrons crossing over into the base. When electrons cross over, some of them will recombine with the holes that are present in the base area, in the base junction, right? And so that's the recombination that takes place here. When recombination occurs, charges disappear. And then there are holes that are moving into the emitter region, right? So you have current flow that takes place. However, the base is lightly doped, and that's the critical aspect of how and why a BJT operates. So the number of holes that are crossing over into the emitter is far smaller than the number of electrons that are crossing over into the base. Now, when the electrons move into the base, are they majority carriers or minority carriers for an NPN device?
Minority carriers.
They're minority carriers. If they are minority carriers, they are now present in the base. So here, they are minority carriers. Here, they are majority carriers. Okay. And now it's a reverse bias PN junction. What happens to minority carriers when you have a reverse bias PN junction? They cross over. And that's why I mentioned this. You have a reverse bias junction. If you have a reverse bias PN junction, minority carriers cross over. And once they cross over, they would be attracted by the external applied voltage source. So in a BJT, if you have connected a positive to the collector terminal with respect to the base, the collector base junction is reverse bias, and the emitter base junction is forward bias. You have a huge number of charge carriers coming from the emitter, hence the name emitter. So a large number of carriers coming into the base, but because the base is very thin and very lightly doped, all those charge carriers are hanging around with nothing to do. But the moment we apply a reverse bias to the collector base junction, these charge carriers that are now present, they're freely present in the base, minority charge carriers, because of the reverse bias, cross over the junction, are attracted by the positive end of that externally applied voltage, and are pulled through into the collector. And a heavy current flow results. Opposite, obviously, current flow for a collector would be opposite in this direction. So the electrons are flowing from left to right. Now we say that the collector current is flowing into the device. And that's the fundamental operation of a BJT. Now let's take a pause. Will you think over that and let me know if you have any questions? Yes. So holes going into the base from where? So base current IB, is that what you're saying? Yes. But because base is very lightly doped, the number of holes is very low. Hence, no matter how much voltage we apply at the base current will always tend to be very small because of the very light doping. There aren't enough charge carriers present. It'd be like applying an electric field to a piece of wood. You can apply a huge amount of voltage, but current's not going to flow. Eventually, obviously, it exceeds and get blocked. So current will flow. Yes, your point is correct that there are holes. The holes will move in response to the externally applied field. But because the number of holes is very low, because of the low doping, the current is always going to remain very small. Yes.
So like the current.
Okay, so you're going to have to repeat that. I know you were thinking out loud, but so we won't talk about the amplifying until much later. But continue with your point. First of all, current's not flowing from emitter to collector. Current's going from collector to emitter. Okay, so electrons are flowing from the emitter to the collector. And so once again, repeat your point. Yes, the base is modulating the current. In a manner of speaking. Well, we're not kind of throwing, they're already present in there. So again, in device physics, the charge carriers are already present. Now, how much they would move depends on the external field, meaning the biasing that we are applying, right? If it's zero bias, they're not going to move. Nothing's happening. If you increase the voltage, meaning you increase the current a little bit, now they're going to move. If you keep increasing it, they're still going to move. They're going to move a little bit more. So the quantity would keep on increasing. So yes, depending how the base voltage, let's say it's an AC signal, it goes up, goes down, goes up, goes down. And so depending on how it changes, the current flow would change. And then the collector current would change. So absolutely, you're correct, right? That's the basic fundamental principle. Current flowing from emitter, between the collector and the emitter, and then the base controls how much is going to flow through. All transistors, all three terminal devices is exactly the same. At its heart or its most fundamental level, we have two primary terminals. We have current flowing between those two terminals like a diode, but we can't control it unless we insert a third terminal. And the third terminal then acts like a, for lack of a better word, like a gate or a valve that controls the flow of the current going from collector to emitter. Now, when we apply this, just going off a little tangent, when we talk about applying a voltage at the amplifying, we're talking about amplifying effects. Your AC signal is going to be very small, millivolts, more likely than not, right? So it's a very, very small signal. And here, between the other two terminals, you're going to apply, let's say, 10 volts, 15 volts, 20 volts, right? And so I like to state it as you have this DC voltage applied between your two terminals, whether it's the gate and, whether it's the drain and source, whether it's the collector and emitter, and then you take your AC signal. That AC signal, the device is going to give the shape of the AC signal to this DC voltage that you're applying. Does that make sense? And that's how we get the amplifying effect. If you apply one cycle of a sine wave, 10 millivolts peak to peak, and you have 10 volts between the collector and emitter, now your 10 volts DC takes on the shape of the 10 millivolt sine wave. And so instead of 10 millivolt sine wave at the input, now at the output, you have a 10 volt peak to peak output.
But the current wouldn't go negative in that case, would it?
Sorry, what was the
the-
comment?
You were saying that if you apply an AC signal to the the valve or the base in this case, that the DC would become an AC waveform.
Well, it's just simplistic way of stating things.
But when the
So-
AC signal goes to negative, then the base would be in reverse bias, so then there would be no current flowing, right?
That is true, but when we bias it in the active region, so it depends on where we bias it. So we are now discussing things that will come later on in this chapter. Basically, there are three modes of operation or three regions of operation. And depending where we operate them, so you're correct, it would become reverse bias, and the device could either go into cutoff, and depending on two forward biases, it could go into saturation. So yeah, that will occur. That absolutely will occur. If you reverse bias the base, the device will go into cutoff, which is something that you will experiment with in lab 8. So yes, you are correct. Yes. So a higher voltage of the base, meaning more current to the transistor. So again, device physics would be important for your understanding. So we'll spend some time here, answer any questions that you may have. And then afterwards, we'll get into circuits and circuit analysis, because that's what you'll be doing majoritarily for 306 and 307 and 308. Okay. All right. Any other questions? Yes.
So why applying this, like if I'm applying a higher voltage of base, then more of the current that's flowing from the heavily doped in type to the less heavily doped in type. I feel like it's almost like
So if we increase the voltage here, you mean? Is that what you're saying? Well, that increase is going to be very, very small. It's not going to be huge. So typically what we'll do is between the collector and emitter, we would have a biasing voltage called VCC. And this VCC, just for practical purposes, let's say here would be 10 volts to, let's say, 15 volts for experiments in the lab. The base voltage would be far smaller. This would be VBB here. Okay. And then VBB would result in a forward bias junction. So what is the value of VBE? Forward bias PN junction. Forward bias PN junction. What's the voltage? Everyone, this is the most important thing, right? If a base emitter junction is forward bias, VBE will always be close to 0.7 volts because it behaves like a true diode. Behaves like a true diode. And that again is due to the differences in the doping. And when we are talking about changes, meaning we are talking about increasing the base voltage, think about it. Once we bias, once we are applying our DC voltages at the base and the collector, an AC signal that comes in is only fluctuating in the millivolts. So when we talk about increasing or decreasing the base voltage, it's a few millivolts. That's it. We are not applying like 10 volts on top of our DC bias. We can try it in the lab, again, lab 8, when you perform, that's the design of a BJT based amplifier. So in that lab, if you apply a large AC signal to your circuit, you're going to get clipping or cutoff at both ends. And you'll be able to see this in the lab itself. So when we say that we are applying, when we are increasing again, repeating the same thing, if we are increasing or decreasing the base voltage, it's going to be very small, very, very small. Yes. Where? Oh, no, that's just the collector to base voltage that's being applied. It's not breakdown. You're talking about this. It's just a biasing voltage that's being applied. That's the voltage being applied between the collector and the base. That's all. Yeah, so it's a NPN transistor. So collector is N type. We are applying a positive voltage to the N-type material and negative to the base, or negative with reference to the base. So VCB is just a notation. That's all it is. Meaning voltage between the collector with reference to the base is higher at the collector or lower at the base. That's all it means. All right, any other questions? So then, here are the important parameters for the BJT, alpha and beta. Alpha is the ratio of the collector current to the emitter current. Remember that IE, the emitter current, is the sum of IC and IB. IB is typically very, very small in microamps. So IE is approximately equal to IC. In some analyses, we will take them equal. Okay, we would ignore IB. Sometimes we won't. So this typically is a value of 0.99 or higher. Okay, 0.99 or higher. And beta IB is the most important relation. This can range between 10 all the way to hundreds. I think 400 or 500. It's defined as the current gain. Now I find beta in terms of each other. Beta is alpha over 1 minus alpha, and alpha is beta over 1 plus beta. Okay, so you can determine the third quantity if you have any of the two. Okay. So I want to do, let's see, page 20. Transport model. So there are several different models we can use for a BJT. I won't get into those today, but I just want to talk about modes of operation or the operating regions. And that is here. So we have the emitter base junction and we have the collector base junction. If the emitter base junction is forward bias and collector base is reverse bias, then the mode of operation is known as forward active. This forward active is also simply known as the active mode. And the reason for that is the transistor is never operated in reverse active mode. Okay. Never or not permitted. It still behooves students to become familiar with the reverse active mode, because if you're performing as an engineer, if you're performing an analysis on a system and the system's not working right, or it's not working correctly at all, then you should be able to recognize if the transistor went into the reverse active mode or not. Okay, that is when both junctions are reverse bias, you get reverse active mode. And then if both junctions are forward bias, you have the saturation mode. And when the emitter base junction is reverse bias, it's cut off. Okay. So the most important takeaway from this table is that the emitter base junction must be forward bias. If the emitter base junction is a reverse bias, and then BJT is off. Okay, you can't do anything useful with it. All right. Okay, we'll end class here today, and I will see you all on Wednesday. Please review today's lecture, and also read the corresponding material in the textbook. Again, the reading assignments are extra credit. The system automatically chooses some questions to assign based on the reading. The due dates on there are simply as a reminder. Okay, the assignments are open for the entire quarter, so there's no penalty or deduction. As long as you finish those reading assignments, you get that extra credit. So read the corresponding topics in the textbook based on the material done in class. Milan, you had a question? Yes. Well, no, saturation is different. Saturation is different for BJT versus an FET. There are different levels, and so depending on the values of IB, we get a set of curves. So there's a maximum value of the current depending on what the value for IB is. But we'll get into that later. Yeah. Yes.
So I was